lectures. So we're going to move on looking at the hydraulic orifice formula, but I'm just going to recap a little bit. Again, we look at gradient, which is pressure difference, which drives fluid from one direction into another. And we derive the modified Bernoulli equation as 4v squared. So the gradient across any orifice, across anything, is 4 times the velocity squared, and velocity across whatever the gradient you're looking at. So you get the velocity, you square the velocity multiplied by 4. And again, by just knowing the modified Bernoulli equation and how to apply it, you can calculate pressure gradients and you can calculate pressures in different chambers. We can do a lot of things. We talk about the right ventricular systolic pressure, show you how to get the pulmonary artery systolic pressure, the left atrial pressure, the PA diastolic pressure, and the LV diastolic pressure. So you familiarize yourself with the modified Bernoulli equation and then know how to use it. So we're going to move on now to looking at stroke volume and cardiac output. When we say stroke volume, what are we talking about? So the definition of these terms are going to be crucial. When we say stroke volume, it is the volume of blood that's pumped out of each ventricle per beat. Okay, so the definition is crucial. The volume of blood that's pumped out of the ventricle per beat. And then when we say cardiac output, it is the volume that is pumped out of the ventricle per minute. So, the two definition varies. And we're going to show you how to use the hemodynamics to calculate or to get stroke volume and cardiac output. So you have to know what we call the hydraulic orifice formula. This hydraulic orifice formula is key. It allows us to calculate flow. So when we talk about flow, and we talk about flow rate, when we say flow rate, then it's the volume of, we're talking about blood now, so it's the volume of blood per time, okay? And we usually say per second. So flow rate is the volume of blood flowing every second, okay? If you just go back to your pipe in your house, when you're talking about water flowing, it's a certain volume, with respect to some time, that is flow. All right. So again, the hydraulic orifice formula is, and we talk about flow rates, is the volume per second, and that is equal to the cross-sectional area times the flow velocity. So if we look at any structure in the heart, we can find the flow rate. All we have to do is get the cross-sectional area. So if you look on the chamber head on, the area, that's the area we're talking about, whatever area that is, and then the flow, the velocity of the blood flow. So if you multiply those two things together, you'll get the flow rate, which is the volume flowing per second. Okay, so we commonly calculate flow rate across valves, and there are 4 valves in the heart, and we assume that the valve area it's circular. That's an assumption. The valve areas are not really circular, but that's an assumption we make because we can if it's circular, we can calculate the area. The area of a circle is pi r squared. So to simplify things, then we assume that the valve area is circular because we know the area for a circle, pi r squared. All right, so that is the hydraulic orifice formula. So again, going back to the original definition, stroke volume is the volume of blood that is pumped out from the ventricle. So let's look at the left ventricle. When the left ventricle contracts, say pump, when the left ventricle contracts, it's going to push blood across the left ventricular flow tract, across the aortic valve, and into the aorta. That's what it does. That's what the left ventricle is supposed to do. When it contracts, it's supposed to force blood across the left ventricular flow tract, across the aortic valve, and into the aorta. Okay, it's supposed to pump blood out of the heart. So we can calculate the flow rate. Remember the hydraulic orifice formula states that flow rate is cross-sectional area times TVI, or the velocity. This formula have the flow velocity. The flow velocity is, okay, you can use either the flow velocity, okay, and you get the flow. But if you want to get the flow rate, really, we put the TVI. And I'm going to, I'll try and explain to you why you can use the TVI as opposed to the velocity. So the flow is equal to the cross-sectional area times the TVI, where TVI, as you remember, is time velocity integral. Okay? So all right. So if we want to calculate the stroke volume, again, you have to constantly remind yourself, what is the definition of the stroke volume? It's the volume of blood that's pumped from the ventricle per beat. All right, so when you have your 5-chamber view, okay, and if you put your cursor at the left ventricular flow tract, and you press PW, you get the left ventricular outflow tract envelope. Okay, it is below the baseline, as we discovered in Doppler, because your transducer is right here. It's your 5-chamber view up top. Left ventricle is right here. When the left ventricle contracts, it's going to pump blood across the left ventricular flow tract, across the aortic valve, into the aorta. So the blood is going to move in this direction, which is away from the transducer. So you're going to get your envelope below the baseline. Okay? Your ECG is on top. It's a systolic flow. So you can, systole is from the onset of the QRS to the end of the T wave. So you come after. So you get a systolic flow. So again, this is your left ventricular flow tract flow. And if you just do planimetry around it, so you just trace around the borders, you get the VTI, which is the velocity time integral. Velocity time integral. What you mean by that? That is what you mean by that is so time is on the horizontal axis, and remember velocity is on the vertical axis. So when you integrate them, okay, so it's like you're multiplying them then. Okay, so basically when you integrate your time and your velocity, you get in, it's like you get in the area under the curve. So you multiply them, and when you multiply them, time and velocity, the time cancels. So TVI is essentially a distance. Okay, so you're gonna get just meters or centimeters, okay? Because you integrate your time and the velocity. So in essence, you're sort of multiplying them to get the area under the curve. So you're going to multiply, again, time. The horizontal axis is in time, and usually time is in seconds, and the velocity, meters per second. So when you multiply them, the seconds cancel, so you get meters. So time velocity integral is in a meter is a distance, okay? So again, stroke volume is equal to the cross-sectional area. The blood is flowing across the left ventricular flow tract. The blood is flowing across the left ventricular flow tract, and it's going to give you this envelope. Okay, this is your LVOT envelope, and when you trace the borders, you get the TVI or VTI. Okay, we're using the hydraulic orifice formula for stroke volume. Okay, so the cross-sectional area of the LVOT, we assume that it's circular. The area of a circle is pi r squared. We can measure, we've been telling you guys how to measure the diameter of the left ventricular flow tract. Remember, the radius is diameter divided by 2. So we could get the radius then. And then if we do planimetry around the LVOT envelope, we'll get the VTI or TVI, whichever, the same thing. And when you multiply them, then you get stroke volume. Remember, cardiac output is stroke volume times the heart rate. Cardiac output, stroke volume times the heart rate. So if someone have a heart rate of 60 beats per minute and the stroke volume is say 50 mLs, so you just multiply the two and you'll get the cardiac output. Cardiac output is the volume of blood that's pumped out of the heart, the left ventricle, per minute. So if you don't have these definitions clear, you won't understand what's going on. Okay, so let's look at some example. Well, let's clarify this further. So again, stroke volume using the hydraulic orifice formula is equal to the cross-sectional area times the VTI. So we're talking about the left ventricular flow tract, which is right here. And we measure the diameter. The diameter is measured in systole. We measure the diameter in systole. So in systole, the mitral valve is closed, aortic valve is open, and a few millimeters in front of the aortic valve, at the tissue blood plane, we measure the LVOT diameter. And this is something that we do routinely in every study. Okay? So we assume that the LVOT is circular. If we assume that the LVOT is circular, the area of a circle is pi r squared. Okay? So the stroke volume is equal to the cross-sectional area times the VTI. So if we're going to simplify for the area, remember pi is 3.14, pi is 3.14, radius is the diameter divided by 2, and if we square that, we get diameter squared over 4, and we simplify that, we get 0.785 times d squared. So the stroke volume, we can use hemodynamics to calculate the stroke volume. That's the volume of blood that's pumped out from the ventricle per beat. Okay, all we need to know is the diameter and then the VTI, because we're going to multiply the area as we showed before. Cross-sectional stroke volume is the cross-sectional area times VTI. The cross-sectional area, when we simplify it, is 0.785 times d squared. And then if you just do planimetry of the LVOT, the computer will give it to you 0.221 meters. So you can convert it to centimeter, which is 22.1 centimeters. So you put that there, and um, you use your, for the cross-sectional area, you use this, what we simplified to 0.785 times d squared. Okay, so it's relatively simple. And then the cardiac output is just the stroke volume times the heart rate. So that is why when the patient comes to the echo lab, you have to do a series of vitals, which include blood pressure, heart rate. But not only that, the computer will store the heart rate with the different frames. So you can see right here, it gives you the heart rate for what you're doing right there. Okay. Again, stroke volume using the hydraulic orifice formula is equal to the cross-sectional area times the TVI or VTI. Cross-sectional area at the LVOT, assuming it's circular, pi r squared, where r is the radius. We usually measure the diameter in the parasternal long axis view. The radius is d over 2, so cross-sectional area is pi r squared. And when we simplified, pi is 3.14. Diameter, radius is radius square, which is d over 2. You square that to get d squared over 4, and you simplify to get 0.785 times d squared. So this, you have to know this, okay, because you need it. So stroke volume is equal to the cross-sectional area times the TVI. TVI is time velocity integral, and that is, you get that from the left ventricular flow track. Okay, you put your PW just a little bit outside of left ventricular flow track. You get your LVOT envelope, and you just trace it, and you get, again, the cardiac output, which is the volume pump out of the ventricle per minute. The volume pumped from each ventricle per minute. So all you do is multiply the stroke volume times the heart rate. So whatever the heart rate is, and you'll get your cardiac output. Okay. We also talk about the cardiac index. If you remember, we always, we index things. And when we say index, we usually divide by the body surface area. So we have normograms that will give you the body surface area for each individual. All you need is the weight and the height. So once you get the weight and the height of any individual, there are normograms that will give you the body surface area. So you divide the cardiac output by the body surface area, and you get the cardiac index, okay? We're gonna, so try and understand this concept, and then on Thursday, we're gonna use it a little bit more, okay? But first of all, fully understand the hydraulic orifice formula, understand stroke volume, and understand cardiac output and cardiac index, okay?